Ladies and gentlemen, welcome to the Big Bear Math channel. We're really happy you're here today, and I'm sure you're working really, really hard to get ready for the AP Calculus exam. You're on a special journey as you're trying to get your college credit and achieve that magical score of earning a 5. Today, we're working through the 2019 BC exam. We're looking at question number 3. It is a non-calculator question, and I think it's going to be right in your wheelhouse. I think you're going to feel very confident on most of this question, if not all of it. And by the time we're done with this problem, we're going to basically take every single rule that has to do with integrals that you've seen in your textbook and put it to use and hopefully see them all come alive here today. So first off, you'll notice that we've been given a graph of f, and it's basically made up of a couple of line segments and then a quarter circle, interestingly enough. So we've got this really nice quarter circle who's centered at 5, 3. So right away, you know the radius is 3. At some point, you're thinking, I've got to probably find the area of that quarter circle, and that's going to be 1/4 pi r squared. It also said that there is a random point here where the x-coordinate is 3 and the y-coordinate is going to be 3 minus radical 5. So we're thinking that's pretty random. They must have given me that for a specific reason. Now, getting set for this first problem, I want to first go over a integral property that you've seen in your textbook at some point. And they've said, let's say I've got a definite integral from a to b of f of x dx. And of course, f is continuous on that closed interval. Well, I want you to imagine a number c that falls between a and b. It could be anywhere between them. Then what I can do is I can kind of subdivide this definite integral into and express it as the sum of two smaller integrals. So we've got the integral from a to c of f of x plus the integral from c to b of f of x. Now, if you're looking at that and you're wondering, I don't know if I buy that, I'm not sure if that's legit, what I want you to do is I want you to consider this graph. Just a real random graph. Maybe here's A, here's B. And that first integral I had was all of this area bounded between that function and the f-axis, or in the x-axis. Now, what we did next is the integral from A to C. Let's say we just pick a random C. Let's put C right here. So here's A, there's C, there's B. Now what we're doing is we're taking this integral here, adding it to this integral over here, and you can see how the combination of those two integrals is equivalent to the original one. So what we're going to do with this problem is I'm going to take the integral from -6 to 5 and kind of subdivide that into the sum of two smaller integrals, and I'm going to use -2 as kind of my split point, or what was my C in this particular problem. So we'll see if we can shimmy up here and create a little space. All right. So what we're going to do is we're going to take a look at, we're going to say the integral from -6 to 5 of f of x dx is really equivalent to the integral from -6 to -2 of f of x dx plus the integral from -2 to 5 of f of x dx. Now, we've got more work than I initially thought ahead of us. So this first integral right here, we already know has a value of 7. All right. This integral right here is the one that we're solving for. So I'm just going to call that question mark right now. And then this integral here is going to be equivalent to the area of all of these little regions up here. So if I go through and we'll just kind of mark what we think all these areas are. I've got a 1/2 here and a -1/2 here. And so basically these triangles cancel each other out. This triangle right here is going to be -1/4. This next triangle here is going to be 9/4. And then the real challenging one here is going to be this odd shape right here. But what I'm really seeing is a square with an area of 9. And then I'm going to subtract that quarter circle from the square. And the area of that quarter circle is 9/4 pi. So this right here is the area of what's underneath that quarter circle. So what I want to do is I want to add all of those bears together. Now adding these two together make 2 plus what was underneath that quarter circle. Try to make sure this doesn't come out too messy. So that is the value of that integral from -2 to 5. So I'm just going to import that down here a little bit. 11 minus 9/4 pi. 11 minus 9/4 pi. All right. And all I want to do is solve for this question mark right now. In other words, the integral from -6 to -2. So really, the integral from -6 to -2 of f of x dx is equal to, so you got to subtract the 11 over and then add that 9 pi over 4 over. And believe it or not, this, and you just want to make sure, well, I guess this answer could be negative. So either way, we're feeling really good about this answer right here. All right, as we jump into part B, I'm confident that no matter what textbook that your teacher has chosen to use in class, that you're going to see these three properties that I have written on the side of the screen somewhere in that textbook. So the first one that I want to point out is this idea, like, let's say I have some constant multiplying the function f of x. You can pull that k out to kind of like, it's almost like factoring it out to the left of the integral sign. Okay, the second one we want to talk about is, what if I have the sum or the difference of two separate functions? What I could do is I could split this up. It's almost like you're kind of distributing the integral sign into the two functions. So you could do the integral of f separately from the integral of f or g, and then just add the two results together. And both of those properties are true whether it's a definite integral or an indefinite integral. And what we're seeing on this third one is what we call the first fundamental theorem of calculus. It says if you integrate f prime, that's equivalent to f of b minus f of a. So I'm going to use all three of those at some point as I solve this problem. So the first thing I noticed right here was I'm going to use this rule right here to kind of split it up. So I've got the integral from 3 to 5 of 2f prime of x dx plus the integral from 3 to 5 of 4 with respect to x. And what you could do is now I could use this rule right here where I basically grab this 2 and slide it out front. So this is going to be 2 times. And now I'm going to use that first fundamental theorem. So it's happening rapid fire here. The integral of f prime is just going to be f of 5 minus f of 3. I'm going to get both of those values from the graph above. Okay, now the antiderivative of 4 with respect to x is going to be the quantity 4x, and then I need to evaluate that from 3 to 5. All right, reading my graph above, f of 5 turns out to be 0, and f of 3 is that really random one, and I believe was 3, was that 3 minus radical 5 or something like that? Yeah. Okay, and I'm watching the parentheses here. Something simple like that gets a lot of great students, because what we're going to have to do is we got to make sure we distribute this negative sign here in a few moments. All right, what we've got over here, substitute the 5 to make 20, substitute the 3 to make 12, and let's see, distribute that negative, then distribute the 2 plus 8. I think I get 2 plus 2 radical 5 for my grand total answer. Hope that made sense. All right, here comes part C. All right, we're going to look for the absolute maximum value of g. G is this newly defined function right here. I like to call g an accumulation function. Anytime you want to find the absolute maximum value or the absolute minimum value, we're going to use something that I like to call the closed interval test. All right, because we're working within a closed interval, basically. So the name is self-apparent there, the closed interval test. And in this test, what I want to do is I want to first find all of my critical points. What are my critical points? Well, that's when my derivative is either equal to 0 or undefined. So applying that second fundamental theorem, I'm going to get g prime of x to be f of x, setting that equal to 0. Let's go back and look at that graph up here and see when exactly is f equal to 0. When is f equal to 0? Let's see here. Looks like a mass chaos here. So we've got -1, +1/2, and then again 5 are going to be the three different times where f is equal to 0. So -1, 1/2, and 5. All right, so x equals -1, 1/2, and 5. And of course 5 ends up being one of my endpoints anyway. So now that I've got my critical points, and those could be potential relative mins or relative maxes, I want to test them compared to the endpoints. And what I'm going to do is I'm going to take each of these values and evaluate g at each of those. Now, in this case, the integral from -2 to -2 is guaranteed to be 0. The integral from -2 to -1 is a +1/2 because of the triangle that sits just above the x-axis. Now, the integral from -2 to +1/2 is going to give you a -1/4. Those first two triangles canceled out, and then you're left with just that little sliver of a triangle that's below the x-axis. And then last but not least, g of 5 is going to be the integral from -2 to 5. And that's basically, again, you're going to add up all those areas, kind of like what we did in part A, and you're going to end up with, I believe it was 11 minus 9 pi over 4. Okay, now we're looking for the absolute maximum value. So you're basically saying, okay, within this list right here, who's the biggest? All right, 9 times pi is going to be approximately, a little bigger than 27. That number divided by 4 is going to make approximately 7. 11 minus 7 is going to make approximately 4. So we're just kind of ballparking it to make sure it's bigger than this number right here. So the absolute maximum value, I've got a real dangerous 2-year-old behind me right here, so who knows what's going to happen in the next 30 seconds. All right, the absolute maximum value is 11 minus 9 pi over 4, and I think that's all we've got to do. Now, that justification they mentioned, that's in the form, basically everything we did there, taking the derivative of g, setting it equal to 0, constructing that table of values was all part of our justification. All right, we're ready to get into D here. When I first saw D, my knee-jerk reaction was, I was betting heavy money that we were going to use L'Hopital's rule. And before we can just blindly start taking derivatives, we've got to first verify that L'Hopital's rule is applicable. And so what I did was I evaluated the numerator here. Now, okay. So looking at the graph up above, the slope of f at 1 is going to be 2. So 10 minus 6 made 4. And I was like, whoa. I was expecting to just, I was just assuming it was going to be 0 over 0. So I was absolutely shocked when I got a 4 right here. Basically, what I know right now is L'Hopital's rule is not applicable. Now, let's go ahead and evaluate the limit of the denominator while we're at it. So we got f of 1 minus arctan of 1. And that's going to produce, now f of 1 up at the top there, from reading that graph, is 1, and the arctangent of 1 is going to be pi over 4. Okay, so if I kind of stack these up, the limit is going to be 4 over 1 minus pi over 4. If you want to kind of clean up that complex fraction, we'll multiply every term by 4. And we'll get this bear. So here's my limit. One of the very, very first limits I've done in a long time that did not require L'Hopital's rule. And again, just kind of remind you, our first option is always going to be direct substitution. So ladies and gentlemen, I'm betting you felt really good about most of that problem, and hopefully you found 1 or 2 nuggets that you can kind of stick in your toolbox and use to get you a little closer to your ultimate goal of earning a 5 on this exam. If you found this video helpful, please hit subscribe at the bottom. That'd be great. And leave a comment, maybe some encouragement or just some tips to help us redo the video and make it a little more understandable. Ladies and gentlemen, have a great night and keep tackling big bears.